My name is Miles, and I am a PhD student in the Department of Atmospheric and Climate Science here at UW. And today I'll be talking about my work predicting coverage and spatial biases in convective outlooks using convolutional neural networks. And again, I'd like to thank my collaborators, Valentina Staneva and my advisor, Alex Anderson Fry, for their invaluable work throughout this project. So, let's see. You can get it. There we go. Yeah, so here's my title, and it's kind of long. It's a bit of a word salad, so we're going to break it down into phrase by phrase. So first, I just want to talk about what is a convective outlook. And before we get to that, what is convection? And convection is not just a setting on your oven. Deep convection in the world of atmospheric science is another word for thunderstorms. And at least big picture, the way thunderstorms form is that either by air masses moving into the right position or just by the sun heating the surface of the earth, you get warmer air below cooler air. So warm air lower in the atmosphere, cooler air higher in the atmosphere. And you may have heard that warm air rises, and that's exactly what's happening in a thunderstorm. That warm air at the surface rises higher up in the atmosphere. And as air rises, it cools down. Cooler air can hold less moisture, so that extra moisture condenses into clouds, forms into rain, falls as rain, and you get your updraft of rising air, and you also get your downdraft of cool, precipitating air next to it. And those updraft and downdraft both separate the charges, both create the charges and separate the electrical charges that can generate lightning. And then also just the updraft and the downdraft help generate all the other characteristics of your thunderstorm. So I also want to talk about what makes one thunderstorm stronger than another. And two key metrics, there's more than just these, but two key metrics I want to look at are CAPE, standing for convective available potential energy. And one way of thinking about that is it's the integrated buoyancy in the atmosphere, or in other words, the total capacity, the total energy that's available for that air to rise up in the updraft. So this CAPE, this potential energy, is directly converted to kinetic energy, and that kinetic energy is the speed of your rising updraft. So more CAPE, which generally happens when you have warmer, moister air lower in the atmosphere and cooler air higher up in the atmosphere, means you have potential for a stronger thunderstorm. And then another really important one is wind shear. Wind shear is simply the vector difference between wind at two different levels in the atmosphere. So that can happen like here on the left. It could be going the same direction, but just faster at a higher level. That will give you wind shear. You can also have directional wind shear. The wind could be the same exact speed at lower and higher levels, but going different directions. And either way, you got this vector difference between the wind at lower and higher levels. And when you have that, that allows the updraft and the downdraft to stay separate from each other. So without wind shear, the downdraft will kind of just go back down and smush down your updraft, and the storm will die out as soon as it pops up. But with enough wind shear, the storm can be longer lived and can develop these stronger structures that lead to a lot more damage. And in general, the central and eastern United States, the traditional tornado alley, and also areas east and southeast of that, have a meeting of air masses, oftentimes from the warm, moist air coming up from the Gulf of Mexico with cooler, drier air coming in from the west and north. And that can give you both your CAPE, your warm air below your cool air, and that can also give you a lot of wind shear. So these areas are very favorable for severe thunderstorms. So a lot going on in this picture. I don't understand. I don't expect everyone to understand everything that's going on here. But just the point being, there are a lot of complex processes at play. There's a lot more beyond just your CAPE and wind shear. But a few of the hazards that are going to be important. First, we have hail. And hail is formed as liquid water freezes onto the hailstone. It grows bigger layer by layer as it's lifted up in the updraft. And then by the time it gets high enough, it's a big chunk of ice that falls out of the sky, can do a lot of damage. We have straight line winds, which are when your downdraft hits the ground and spreads out. So you have a big gust of wind that, again, can do a lot of damage. And then finally, you have a tornado. And a tornado forms when rotating air in the atmosphere is tilted vertically and stretched out, intensifying that rotation. And as we all know, tornadoes can be very damaging as well. And in general, all three of these hazards, not 100% of the time, but they tend to be stronger in a more extreme environment where you have more CAPE, more wind shear, more low-level moisture, and so on. So I also want to talk a little bit about storm structure, and we can see a big variety of storm structures that depend a lot on the environment, on the exact profile of the winds in the atmosphere, the exact profile of temperature, of moisture. Yeah, a lot of different factors, but you can end up with single cell thunderstorms, multi-cell storms. A supercell might look like this one at the top. That's kind of your most traditional textbook tornado producing storm. You can also get mesoscale systems like a squall line down here that are larger, longer, can produce especially widespread wind. But yeah, just important point is that there's a lot of variety, a lot of different structures, a lot of ways we can get damage from thunderstorms. But across any of these structures, we define a severe thunderstorm as one that produces hail of at least 1 inch diameter, wind of at least 58 miles per hour, or any tornado. And on average in the US, these severe thunderstorms cause about 50 deaths and over $10 billion of damage per year. So we want to forecast these storms as well as we possibly can to help get people and property out of harm's way. All right, so hopefully that answers what convection is. So now we're going to look at what are convective outlooks. And in general, when we're forecasting these storms, there's a couple big challenges that make it difficult. And the first thing is that when you run a forecast model, the forecast models that make the weather forecast on your phone, these models treat each grid square as its own kind of point. So when these models run, everywhere in this one grid point is going to have one single temperature, one single pressure, one single amount of rainfall, and so on, representing what's happening in that grid square. But a thunderstorm, and especially a tornado, hail, rain, is happening on a much smaller scale than a single grid point. So we actually need to come up with parameterizations or ways to get from the more general environment that we're estimating in that whole grid square to is a thunderstorm going to happen in a smaller point in that grid square. Another challenge is that convection is inherently chaotic. And by that, I'm going to do a little thought experiment. So imagine you put a pot of water on the stove and you crank up the heat, and I ask you, where in that pot is the first bubble going to pop up? And you're not going to be able to tell me. It could happen anywhere in there because that's inherently random. It depends on a lot of chaotic processes. And that's kind of analogous to what we have going on with thunderstorms. You can imagine when you have the right conditions for storms across, say, like Texas and Oklahoma, you can imagine turning on that heat under the state, and we know thunderstorms are going to pop up somewhere, but you don't know exactly where that's going to happen. But luckily, through a lot of study and the great work of many scientists, we do know what environmental conditions make thunderstorms and severe thunderstorms more likely. So forecasters look at maps like this, and again, you don't need to understand everything that's happening here, but you look at temperatures, at moisture, at wind, at that cape and that wind shear that we talked about, and we come up with pretty decent predictions of where thunderstorms are going to happen. And more formally, this is done with a convective outlook, and that's a product that's issued by the NOAA's Storm Prediction Center. And a convective outlook is a daily categorical risk level map for thunderstorms across the contiguous United States. And these risk levels go from level 1 up to level 5. And this is one example. And on this day, May 20th, 2019, we have a high risk here in kind of northern Texas, western Oklahoma, and decreasing risk levels around that. And we have up to a slight risk up in the far northeast. So throughout this project, any single day examples are just going to be for this day to keep it consistent. And I also do want to point out these forecasts do go out to 8 days of lead time, but everything we're looking at here is the day one outlook, which is just the forecast issued the evening before the day at hand, or the evening before the forecast, the day we're trying to forecast. So we also have probabilistic convective outlooks, and that's more specifically what we're studying today. And a probabilistic outlook forecasts the probability of seeing your specified hazard, whether that's wind, hail, or tornadoes, within 25 miles of any given point on the valid day. So, for example, if you were here in central Kansas, this tornado probabilistic outlook is telling you there's a 5% chance a tornado will occur within 25 miles of you on this day. And then this forecast is saying there's a 15% chance in this yellow area, severe wind will occur within 25 miles of you, and so on. And there is a systematic way that we go from these probabilistic outlooks to the overall category. We're not going to worry about that for today. We're working entirely with these probabilistic outlooks. So we have our forecast, and then the day comes, the storms happen, and this is May 20th, 2019 again, and it looks pretty decent at first glance. The storms are generally happening around that area of highest risk. And these storm reports come from trained public spotters, and they're validated by the Storm Prediction Center as well. And this is the best data set that we have for validation to use as our ground truth. But there are some known issues. It is definitely an imperfect data set. We want to keep that in mind. The biggest, most obvious thing is that if a thunderstorm happens, produces hail or wind or a tornado, and no one's there to observe it, it doesn't get entered into this database. And this varies a lot over space, over time. In unpopulated areas, a storm might not get reported at night. It's less likely to get reported. And even over time, more storm chasers have gone out to try to find tornadoes would be another example. So there are inconsistencies like that. And we also know another systematic problem is over-reporting of subsevere wind. And by this, I mean a thunderstorm can produce a wind gust that's not up to that 58 mile per hour standard, but it could snap a tree branch. Someone reports that and gets entered into the database as a wind report of unknown speed. So often in the east, southeast, northeast United States, where there are a lot of people and also a lot of trees, you can end up getting a lot of these extra wind reports that aren't necessarily representing really how severe and how damaging the storms were. All right, so now we know what convective outlooks are, and I'm going to talk about what are coverage and spatial biases in these convective outlooks. And these aren't formalized terms. These are just kind of two ways of measuring bias that we've been developing. So first, I want to talk about coverage bias. And coverage bias is pretty simple. It's just the forecast minus the observed number of grid points at which storms are reported within 25 miles. So again, looking at our example day, here's our forecast. Here are the observations. And this is just the wind probability forecast. So if you break that into 25-mile grid spacing grid and just count up all the grid points, if it's in a 15% probability, that adds 0.15 to your total expected number of storms. You get 33.23 total storms or total wind grid points with storms nearby expected on this day. And in reality, there were 32 of these grid points that had a wind report within 25 miles. So our coverage bias on this day for wind is 1.23. That's pretty close to zero. That's pretty good. Our wind forecast on this day was calibrated relatively well. Next, I want to talk about how we get spatial bias. And this is using an optical flow algorithm. And optical flow is the vector field of apparent motion between two images. Traditionally, these would be two consecutive frames in a video. So in this example, we could have a video of cars driving along the road. And in the next frame in the video, the cars are going to be a little bit lower and further left in the frame. So our optical flow algorithm determines that the vectors at those cars, which are these little blue arrows, they might be kind of small, but those vectors are pointing to the lower left to represent that direction of motion. And again, this is traditionally a computer vision tool, but it has been applied in the atmospheric sciences before. And for our purposes, we're applying that optical flow algorithm between our outlook field and then a smoothed version of our observations to find our vector difference. That's essentially how you need to move that outlook in space to get it to look like what actually happened. And again, a lot going on here. A lot of vectors, so I find it helpful to look at one specific area. And we can look at Missouri here. And in the forecast, the storms are reaching into the far southwest corner of the state, when in reality, storms reached further northeast than that all the way to the northeastern reaches of the state. So in our vector field, the vectors in that area are pointing to the northeast to represent that things happen further that direction than we expected them to, according to the convective outlook. So we can take a mean of this vector field to sum up the day into two single values, the two components of that overall vector field. When we do this average, we are weighting by the outlook probabilities, A, to capture the most important areas that are doing the most damage, and B, to also just avoid capturing some artifacts of the algorithm, like this over here, for instance. But yeah, on this day, we get a positive northward and a positive eastward component of our vector field. So we can do this for every single day and look at the distribution of those averaged vector fields for wind, hail, and tornadoes. And across our data set, 2002 to 2023, we see that wind more often than not has a southeastward displacement. So that's saying wind is more often than not happening to the southeast of where it was forecast to in the convective outlook. And oppositely, hail tends to happen a little bit to the west of where it was expected to in the convective outlook. And tornado doesn't have quite as much of a systematic bias. And one potential explanation for this is that if we think about how storms evolve throughout the day, in the most like textbook kind of on average setting, this isn't always true, but more often than not, you have storms that pop up earlier in the day, kind of midday, mid-afternoon, and these storms initially start as single cells that are good at producing hail. And as they move eastward with the overall flow of weather throughout the day, they tend to conglomerate, they tend to grow upscale into more widespread storms that are better at producing wind. And also, you're a little further east away from the higher terrain of the Rocky Mountains, so more time for hail to melt. You might also get a few less hail reports. So it does make sense that wind is happening east of where hail is happening. And this is known. The forecasters, the SPC, are very aware of this. So the hail outlook is generally centered a little bit to the west of where the wind outlook is centered. But these results are suggesting that not enough is being done to differentiate those outlooks. So we can also look at some trends over time of these different bias types. The first, second, and third column are for wind, hail, and tornadoes, respectively. And then from top to bottom, we have our coverage bias and then our two components of directional bias. So for all three hazards, there's been a trend toward under forecasting over time. So that's the forecast number of storms in convective outlooks has been shrinking, while the observed number of storms is not showing that same trend. And we also see an eastward trend for tornadoes, and that westward bias that we saw for hail earlier has been shrinking over time. But I do want to point out a lot of these trends are, at least in large part, non-meteorological. There have been well-known changes in forecast practices and also in observational practices that have led to different forecasts, different observations when a climate trend may be present here, but it may not be quite as visible over those observational trends. And this brings up a lot of bigger questions of like, what should even the goal be when creating a convective outlook? Are we trying to be as accurate as possible with our probabilities? Are we trying to save as many lives as possible? Do those have to be the same thing? Or are those compatible? Are those different? Would those lead to different outlooks? But yeah, a lot of fun philosophical questions, but in the interest of time, we'll be moving on to the next stages of our project. So now we know what convective outlooks are, and we also know what these coverage and spatial biases in those convective outlooks are. And now the meat and potatoes, I want to talk about how we predict those biases using convolutional neural networks. And kind of framing our question here, what are we trying to do? Everything I've shown so far has been data set wide. We know that more often than not, hail is happening west of where it was forecast. So this is, I guess, wind as an example. Wind's happening southeast of where it was forecast a lot. But what would be even better, what would be a lot more helpful, is to understand or be able to predict, be able to know what bias can we expect on any given day. If we know the synoptic environment, or in other words, if we know what the overall weather patterns are for a day, what bias can we expect to see? So on what days is wind going to happen west of forecast? On what days is it going to happen east of forecast? And so on. And the first sort of most direct approach, head-on approach, was just to subset the results and see what environments correspond with our different biases. So on these plots, the left one is our temperature and wind barbs on average for the 1/3 of days where tornadoes are happening most to the north of where they were forecast. On the right is that same composite for the 1/3 of days where tornadoes were happening most south of forecast. And you might be able to like pick out some small differences here, but I don't think these are especially insightful, even if you recenter them and see a coherent pattern around a low pressure system. If you're interested in that kind of thing, we're still not seeing like a whole lot of super meaningful difference just looking at those. So what would be even better is to train a machine learning model that can predict what our biases will be from the environment. And yeah, we're going to lay out the concept of our model right here. So the model takes as input a gridded data set of Era 5 reanalysis. And if you don't know what Era 5 reanalysis is, it's basically our best guess at the weather conditions, at the state of the atmosphere across the Earth since 1950. And by gridded, I mean this data set is on a quarter degree by quarter degree grid across the entire globe, which I think is like 30 kilometers by 30 kilometers. So at any one of those grid points, this data set tells us every single hour since 1950 what's our best estimate of temperature, of wind, of moisture, and so on, both at the surface and at many levels going up through the atmosphere. So our model is going to take that snapshot, that state of the atmosphere during a day. It's going to run it through the convolutional layers, and then it's going to predict the three biases, the coverage bias and those two components of directional bias, predict what those biases will be on the day with these weather conditions. And that gives us three values. I guess we have those three biases times there are three types of hazards: wind, hail, and tornadoes. So our model is trying to predict 9 different target variables. So there are 9 scalar values that our model is trying to predict for any one day. And ultimately, the idea here is our model can basically look at a snapshot of a day's big picture weather conditions and say, oh, I've seen this before. On days with these conditions, the forecasters at the SBC have tended to under forecast the amount of hail, for instance, or the forecasters have tended to forecast tornadoes too far east, or things like that. So to dig a little bit more into our input data, again, this is our Era 5 reanalysis. It's representing the environmental conditions during the day at hand. And we have these 4 variables at the surface. And then we also have these 6 variables at pressure levels, multiple different pressure levels going up throughout the atmosphere. So we have temperature. We have variables capturing the amount of moisture in the atmosphere. We also have variables representing the wind or the movement of air in the atmosphere. Yeah, those are the pressure levels that the pressure level variables are at. But every single variable level combination, so essentially temperature at the surface or temperature at 500 hectopascals, temperature at 700 hectopascals, and so on. We have these 4 surface variables and then 6 pressure level variables times 5 levels gives us 34 total different variables or total channels. If you're familiar with convolutional neural networks, the most traditional use of these is image processing, and a network processing an image has generally 3 channels. It looks at the red, the green, and the blue components of the overall image. So our model is going to be looking at 34 different channels as its input. This data set in total is 5-dimensional. It's latitude by longitude, by time of day, by those 34 channels, and then all of that on every single day in our data set. And I want to point out why time of day and date are different dimensions here. And that's because we're treating each day independently. So our model is trying to make a prediction for any one single day. And within that day, the model is looking at multiple hours of the day. But our model is never taking a continuous time series across multiple days at any point. And then we process this data just for computational stability to have mean 0, standard deviation 1. So I want to expand on our dimensions a little bit more and build it up from the base just to really lock down our understanding here. So this is going to be a 2-dimensional field. You could imagine it was, let's say, the surface temperature across this portion of the United States. And that has 2 dimensions, latitude by longitude. And that's just one snapshot in time. But we could also imagine you have that same field over multiple steps. I guess this would be 4 different hours in time. And this means you have a 3-dimensional field, latitude by longitude by time of day. And when I say we're using a 3D CNN, 3D convolutional neural network, these are the 3 dimensions that I'm referring to. So traditionally, a CNN, if you're familiar, has its little filter that gets passed over our 2D image, just a little 2D filter. This instead has a 3D filter that's learned and passed over our 3-dimensional tensor, I guess it would be. So now The fourth dimension, our little blue image there was just surface temperature, but you could have temperature at every different level, pressure, you could have moisture at every different level. We have all our different channels. So that's going to be the fourth dimension. And then all of this is for a single day, but our model is going to make a separate prediction for each day. So we could say our fifth dimension is day. All right. Now moving on to our target data and how that's processed. As we've mentioned, we have three hazard types. We have wind, hail, and tornadoes. And then we have three types of bias: coverage bias, north, and then the north-south and the east-west components of our directional bias. So our model is trying to predict 9 scalar values. And just looking at 3 of those 9, so these are the coverage and spatial biases for hail. And then we saw these before, but these are our time series of those values from 2002 to 2020. And we did a couple things to this. We removed the linear trends, and we also standardized these data sets to have mean 0. And what that does is essentially saying, if we know there's systematic biases, going back to our example of hail is always, hail is tended to be forecast hail happens west of where it was forecast, but that's shrinking a little bit over time. We're essentially removing all of that, recentering on that, and getting these data sets that have mean 0 constantly over the time period and have a standard deviation of 1. And another consequence of this is that we can imagine a really dumb model, a really bad model. And this model is so bad, it doesn't even look at the input data. It doesn't even look at the reanalysis data, the environmental conditions. It just jumps ahead. It's excited. It makes a prediction. And the best that this model can do is just predicting 0, because our target values are always centered at 0. And because they have a standard deviation of 1, the mean squared error for this really stupid model is going to be 1. So we can think of this as like a 0 skill baseline. Mean squared error of 1 is our baseline, and we're trying to make a model that has a lower mean squared error than that. And I'll also say that since we're trying to improve on the forecasts that are made by many scientists who have put many years of work, many years of expertise at the Storm Prediction Center, we can't expect to drop that mean squared error super low, especially when there's just a lot of inherent uncertainty in forecasting thunderstorms. So going for mean squared error, a bit less than 1. So just to touch on some model architecture details, we're using from 2 to 4 3D convolutional layers in our networks. And then we also have one fully connected layer at the end. And we also tune different hyperparameters. So not only number of layers, layer size, but also batch size, learning rate optimizer. And for results, we're just going to be showing the models that perform best. But performance was pretty similar across all reasonable choices of these hyperparameters. We also broke our data set from 2002 to 2019 as our training data set, and then 2020 to 2023 as our test data set. And we actually have not touched that test data set yet because we're still developing the models. And all of our results, all of our validation is coming from 5-fold cross-validation within our training data set. And the way that works is essentially splitting 2002 to 2019 up into 5 random groups of days, and then training 5 different models. Each model is trained on 4 of those groups and then tested or validated on the 5th group. And then averaging the performance across those is a good estimate of model performance overall. All models were trained for up to 50 epochs on GPU on NCAR's derecho supercomputer. Optimal performance was usually before that, but we trained for up to 50 epochs. And we also used, as I mentioned, a mean squared error loss function. So I'm going to get into some results now, but I do want to frame this a little bit by breaking down a few different classes of models that we trained. So we have 2 columns and 2 rows here, and each intersection of those is going to be one type of model. So some models were trained on the full ERA 5 inputs. So that's quarter-degree spatial resolution, hourly time resolution, and across the entire United States. So we're giving it all of that information about the environment. But some models were trained on a lightweight version of that. So this is thinned out to have just 1 degree spatial resolution, 6 hourly time resolution, and only in this smaller box that doesn't even contain the full US, that doesn't even contain all the storm reports, but it does contain where a large, I don't know if I would say majority, but a large portion of our storms are occurring. And then separately, breaking it down this way, some models were trained on just moderate risk and higher days. So moderate risk are those more extreme, more impactful days. There were 360 of them total across our 20-year data set. Some models were trained on slight risk and higher days, which is a little bit of a lower standard, bigger data set. There were about 4,000 days falling in that category. So now we're going to reveal our mean squared errors. First, I want to remind everyone again that our baseline, we're trying to do better than a mean squared error of 1. And for the model trained on those lightweight inputs on moderate risk and higher days, our mean squared error was 0.94. And then for a model trained on the full inputs on moderate risk days, mean squared error was 0.96, which was a little bit surprising at first that a model given more data, more information, it should be able to do better, but actually did not do any better than the model trained on lightweight inputs. I will get into why that is later. And then for models trained on slight risk and higher days, that bigger data set, our mean squared error got down to 0.9. And then I don't have a number here, but I will say when we were training with a little bit of a different configuration for our target variables, that wasn't the exact same, so we can't put the exact number up with these. That performance was, again, not any better than the model trained on lightweight inputs. And that model is very heavy, takes multiple days to prepare and train. So seeing that consistent pattern, we're not wasting our time training that model. So looking at our best model that has a mean squared error of 0.9, using these lightweight inputs across all slight risk and higher days, we can also break down how the model is doing on different variables. So this 0.9 is average across all 9 of our target variables, but we can look at each one individually. So I'm going to put up some plots here. There's a lot going on, so I'll try to walk us through it. Hopefully we can understand everything that's happening. So first, we see 9 different bars here, and each of these 9 bars is one of our 9 target variables. So from left to right, we have wind, hail, and tornado for a coverage bias. And then again, those 3 variables for the east-west component of displacement bias, and then the north-south component as well. So we're just going to zero in on this first bar, which represents the bias, the count bias for wind outlooks. And then the same idea will apply to all of them. But I find it easiest to start with the orange bar. And the orange bar, if we remember that really dumb model that predicted 0 every time, that corresponds with our orange bar. And I also do want to point out the units, the y-axis has been converted back to the kind of original units of bias and is now root mean square. But yeah, so the orange bar is representing that model that predicts 0 every time. So yeah, I guess to back up then, we can go up to the blue bar. And this is a model, hypothetical model, that also predicts 0 every time, but it's doing that before the detrending, before the demeaning. So the blue bar is essentially representing the expected bias that you would get in the original outlooks issued by the Storm Prediction Center. Then if you go down to the orange bar, that's the expected bias you would get by just applying like a mean data set wide bias correction. So with our hail tending to occur west of where it was forecast, if we just correct that across all the outlooks, that gets us down to the orange bar. And then the green bar is the performance of our model itself. And that's what's actually being learned one day versus another. When one day is, you can expect one type of bias on one day, the model expects a different type of bias on another day. That's where the skill is really coming from. So to look at some of these results, we see both for coverage bias and directional bias, we see that the model is doing best for wind. And another surprising thing is that we didn't really expect to see this north-south component of wind directional bias to show such an improvement in the model. The model is doing really well there. Now it's pretty surprising because if you look at hail, east-west, there is a gap between that blue and orange bar. So there is a sort of systematic problem. And then going lower than that is figuring out when that systematic problem is happening. For north-south displacement for wind, the model's doing really well, even though there is no systematic data set wide bias that we're identifying. So some general takeaways, and I think some of these lessons can apply to other work as well. But some scenarios where the mean squared error showed not a whole lot of change. First, as we mentioned, just modifying the hyperparameters and model architecture, as long as the choices were pretty reasonable, didn't show a lot of difference. I think that's saying that there's not like going to be one special model that somehow performs better than all the other ones. Another thing to note is that at one point we were actually training during using input data that was shifted 12 hours too early. So the input data was for one single day was kind of starting 12 hours before the validation period, before the storms reports were being counted up, and then ending 12 hours before that period ended. And the models actually didn't do a whole lot worse in that scenario, which I think is suggesting that the model, whatever it's learning, is something big picture, something that's still present in the atmosphere a little bit ahead of time. And along that same vein, our models perform pretty similarly, and even a little bit worse when using that higher resolution data that theoretically should have more information to pull from. But I think that is suggesting that whatever the model's learning, it's learning something pretty broad scale. It's learning something synoptic, something general, rather than like little tiny details at any one grid point. And adding more detail that the model's not really using is just confounding. It's just more calculation, more ways for things to go wrong. Those models took a lot longer to train, a lot longer to use as well. And then finally, earlier on, we were using this unnecessary kind of artificial all hazard target variable that was just all three of those different hazards combined, summed up into one. And the model did predict that variable pretty well, which we were expecting. But the good news is when we got rid of that, the model started doing better on hail, wind, and tornadoes all on their own. So I think that's kind of a lesson, even though an ML model, like theoretically, it should be able to do anything. Theoretically, it should be able to predict that extra variable in addition. It's often best to keep it as simple and just work with what you really need. All right. I also want to talk a little bit about the next stages of development for this model with a shaft distribution, and I'll get to what that means. But to introduce this, I want to do a little thought experiment, which is that you can imagine it doesn't matter what it is, but imagine there's some type of weather pattern, some type of flow that's happening across the country. And when this weather pattern happens, the forecasters of the SPC, they usually do a pretty good job on the median or on the mode. There's not a whole lot of bias in their convective outlooks. But occasionally when this pattern happens, there's very few storms. There's way fewer than expected. So our coverage bias is really, really high. And our current framework, where we're just predicting a scalar value, isn't going to do anything to capture this. All it's going to do is predict the one value as best as it can. But what we can do is, instead of predicting a single value for each target variable, we can predict 4 values that specify the Shash distribution. And the Shash, you can think of it as pretty similar to a normal distribution. It has a mean, it has a scale, which is analogous to the variance, but also has a skewness and also has a tail weight. So I like this green bar, or that green little distribution down here as an example. The model might predict that green distribution for coverage bias, and that long tail is saying we think it's going to be around this number, but there's a chance it's a lot higher, but there's not really any chance it's a lot lower than that. So the way we implement this, the biggest change we need is we can't just use a mean squared error. That doesn't work in this framework. Instead, we have to use a negative log likelihood loss function. Put the math there, but I think the best way to explain this is looking at some pictures. So for this is kind of 3, each blue line is a hypothetical distribution that our model has predicted. And all 3 of these distributions, it's predicting a little bit to the left, a little bit too low below our true value, which is represented by the pink dotted line. In the first distribution, the model is predicting a really narrow distribution, and that means the likelihood of the true value falls really low on that line, so our likelihood ends up really low. If our model predicts a really wide distribution, our likelihood also ends up pretty low. But if the model is calibrated correctly, if it predicts a reasonable width on that distribution, that's going to give us the highest likelihood. And then we just take the negative log of that as something to minimize as our loss function. Another useful thing we can do here, when we were using mean squared error, we had that exactly one baseline that we were comparing our results to. That was kind of a no-skill baseline to improve from. And here we can use a normal distribution with mean 0, standard deviation 1 as our zero-skill baseline. So you can imagine, again, like a dumb model that doesn't even look at the target data. It just predicts mean 0, standard deviation 1 all the time, which is the true distribution of our targets, but it's not predicting a different value for any one day. And if you take the expected value of the negative log of that likelihood, it comes out to 1.42 nets, which is a unit of information. So we just have some preliminary results now, but this is comparing that zero skill baseline of 1.42 to our model loss. We've just trained a few models, but some with moderate risk and higher, so that smaller training data set, and then some on that larger slight risk and update data set. And that moderate risk data set, we're just seeing a marginal improvement over that baseline. But on that slight risk data set, we're seeing a much more substantial improvement. I am really excited to get into this, to break this down and see which of our different target variables the model is doing really well on, and also what types of distributions is it predicting? Is it predicting something that's really not normal, not standard in certain situations? And yeah, just see where that skill gain is coming from. And then finally, I just want to touch on some more future work that we're hoping to do, which is using some explainable AI or XAI methods here. And right now, as things are, we have a little bit of a black box model. We just give it its inputs, it tells us the outputs, and that's useful as a tool, but it doesn't provide quite as much process-based insight to what's happening. So we could use some XAI methods, the first one of which is attribution heat maps. And there's a few different examples here, but these are all different attribution heat map methods applied to some convolutional neural network that was doing some kind of image processing on this picture of a dog. And what all these methods are doing, put simply, is highlighting the areas of the image where our model is doing most of its learning from, the most important areas. So in our framework for what we're doing, if we apply some of these methods, we may be able to highlight the certain areas, the certain regions, and also the specific variables that our model is actually able to learn from, and see what's most important. And that could provide some insight into what's actually happening in the atmosphere. And then another method is activation maximization. And this is essentially creating the input that leads to the most extreme output, for the most positive or negative of any one of our biases. And doing this could kind of create like a hypothetical environment that would be expected to give the greatest or least of any one of our biases. And that could be insightful as well. And then finally, we just want to do some lower tech, some more manual investigation, and just messing around with the data, making some plots, seeing what other information we can pull from it. So that's all.